So with these center of mass problems, you can actually use other physics things that we've learned in the past, which is pretty much true for all of these physics concepts we learn. But you can apply them to your center of mass equations. And what I mean by that is when we have a problem like this, basically you'll see that I have my position for the center of mass, that equation that we've learned in this chapter so far, but then also I'm going to bring in kinematics with that and kind of substitute in equations for kinematics, and you'll see what I mean. So we have a 1,000 kilogram automobile is at rest at a traffic signal. At the instant the light turns green, the automobile starts to move with a constant acceleration of 4 meters per second squared. At the same instant, a 2,000 kilogram truck traveling at a constant speed of 8 meters per second overtakes and passes the automobile. A, how far is the center of mass of the automobile truck system from the traffic light at t equals 3 seconds? And B, what is the speed of the center of mass then? So let's write down our givens first. I'll call this mass 1 is 1,000 kilograms. And then I know that it's sitting at the traffic light, so the initial velocity of mass 1 equals 0 meters per second. I also know that it has an acceleration, I'll call this of mass 1, of 4 meters per second squared. Now they also tell me that mass 2 is 2,000 kilograms. And it is traveling at a constant velocity 2 of 8 meters per second. And then, of course, we're looking at this whole thing with the time of 3 seconds. So we want to find the position of the center of mass at 3 seconds and the speed of the center of mass at 3 seconds. So we know that our center of mass position equation is position of center of mass is equal to mass 1 times position of mass 1 plus mass 2 times position of mass 2 divided by mass 1 plus mass 2, because here we only have 2 masses. Now, of course, we know a lot of information about those 2 masses, but we don't know the position at 3 seconds of mass 1 and mass 2. So in order to find that, what we're going to do is we're going to use kinematics. Now, I know that I have an initial velocity of 0 for mass 1. I also have an acceleration for mass 1 of 4 meters per second squared, and then I'm evaluating it at a time of t equals 3 seconds. So I know that if I have those things, I can use the equation delta x of mass 1 equals initial velocity of mass 1 times time plus 1/2 acceleration of mass 1 times time squared. Of course, here my initial velocity is 0, so that whole term cancels out. And then also my initial position of mass 1, I'm going to call 0 as well. So because of that, I get final velocity of mass 1, final position of mass 1, which is going to be my x1, is equal to 1/2 acceleration of mass 1 times time squared. Now for mass 2, I know that it is going at a constant velocity. So the velocity of mass 2 is equal to our delta x2 over time. Again, for delta x, that's final position minus initial position. And we'll say that at that time t equals 0, that's when mass 2 is passing mass 1. So that means the initial position of mass 2 is also 0, which means that I end up getting, if I solve this equation for my x final of 2, I get v2 times time. So now that I have 2 equations here, I can plug them into my original equation. So I have the position of the center of mass of the 2 objects are mass 1 times this whole thing, 1/2 acceleration of 1 times time squared, and then plus mass 2 times this whole thing, position of 2, which was v2 times t. So that goes here, and then that came from here. So obviously I'm also going to divide by mass 1 plus mass 2, and then I'm just going to make this a little bit prettier. So I get position of the center of mass is equal to 1/2 mass 1 times acceleration of mass 1 times time squared plus mass 2 times velocity of 2 times time divided by mass 1 plus mass 2. So now I can plug in my numbers here. We get the position of the center of mass is equal to 1/2 times mass 1, which is 1,000 kilograms, times acceleration of mass 1, 4 meters per second squared, times 3 seconds squared, plus mass 2, 2,000 kilograms, times velocity of 2, which is 8 meters per second, times time, 3 seconds, all divided by 3,000 kilograms, because 1,000 plus 2,000. So for this, when I plug this into my calculator, I end up getting 22 meters for my position of the center of mass at time t equals 3 seconds. Now, for velocity, I know that velocity is equal to the derivative of the position equation with respect to time. So because of that, I can take the derivative of this equation up here. Okay, so I'm going to take the derivative of that equation with respect to time. Now, if I'm taking the derivative with respect to time, I'm going to take this exponent right here. I'm going to multiply out in front by that exponent and then subtract 1. Of course, mass of the car and acceleration of the car is not changing, so those are constant. The only thing that we're looking at is time here as our variable. So I end up getting 2 times 1/2, which is just 1. So we get mass 1, acceleration 1 times time, plus, and then of course the exponent for that second time right there is 1. I'm multiplying that whole thing by 1, subtracting 1, so I get t to the 0 power, which is just 1. So the derivative of that is m2 v2, and then of course I'm still dividing by m1 plus m2, because those are constants as well. So this is my equation for velocity. And then plugging in my numbers here, we get velocity is going to be equal to, and this is the velocity of the center of mass, that's equal to 1,000 kilograms, mass 1, times acceleration of mass 1, 4 meters per second squared, times time, 3 seconds, plus mass 2, 2,000 kilograms, times velocity of 2, 8 meters per second, divided by the total mass, 3,000 kilograms. So for velocity of the center of mass, we end up getting 9.3 meters per second for our answer.